Okay. Insignificant T ratios. Okay. Let me see whether all of you are online. Okay. Right. Okay. So when correlation between the regressors increases, you see what is happening to these confidence intervals. The confidence intervals are becoming wider. Wider का मतलब ये होता है that the lower limit and the upper limit of the 95% confidence interval for beta 2, the lower and upper limit would become away from each other. So when the interval become wider, right, uh, there are more chances that the null hypothesis of no effect may not be rejected. यानी ये जो zero null hypothesis है वो क्या है? H naught beta 2 equal to 0, right? There are more chances that 0 would lie inside these intervals. So therefore, you may end up with concluding that there is no effect of the corresponding x variable on the y variable, while maybe actually it is not the case. Insignificant T ratio का मतलब ये है कि if you recall the T ratio, okay, okay, let me quickly just verbally explain these things, and then I would like to quickly go to stata so that you can practically understand what I'm talking about, right? Because otherwise it would not make sense. X insignificant T ratios का मतलब ये है कि the T ratios may be actually significant, okay? In the last lecture, if you recall, we said that the T ratio is simply the ratio of coefficient to the standard error, okay? T ratio is the ratio of coefficient to the standard error, okay? So for example, in the stata output, if I could show you that, this T ratio that you can see over here, right? Like for example, this T ratio. How you obtain this T ratio? This is just this coefficient divided by this standard error. Minus 63.0971 divided by 87.45276. The ratio of coefficient to standard error, right? This gives you the T ratio. So you see this when you are defining T, okay? So T is actually the coefficient, right? This one, right? Divided by the standard error. So the coefficient divided by the standard error. Now, when there is a case of high multicoronarity and when the variance of the ORS estimator increases, so what happens to this standard error? This also increases. So when standard error increases unusually, what would happen to this T? You see, the standard error is occurring in the denominator. So when this standard error increases, what would happen to this T? This T would come down, right? So there is an inverse relationship between T and standard error of the ORS estimator. The larger the standard error, the smaller would be T. So when the standard error becomes larger and larger, a point would occur when T absolute, which means ignoring the sign, when this would become less than 2. When this would become less than 2. Okay. And you know, this is what we call the rule of thumb. Like when the T ratio becomes smaller than 2, ignoring the sign, then we call it an insignificant T ratio. So because of high multicoronarity, it may happen that the standard error becomes so large that it will make your T ratios quite small. And as a result, when the T ratio becomes smaller and smaller, the P value becomes larger and larger, right? Usually when the T ratio is less than 2, then the P value would be more than 0.05. And you will conclude that there is no significant effect of, for example, MPG on the price of a car, okay? But you may not be sure whether this insignificant P value that you are getting here, or whether this insignificant T ratio, right? Because ignoring the sign, the T ratio is 0.72, which is less than 2. So you may not be sure whether this insignificant T ratio is a really insignificant T ratio or whether it is because of multicoronarity, right? So there is every chance that you may be wrongly concluding that there is an insignificant effect of MPG on price, while actually it may not be the case. Maybe there is a significant effect of MPG on price of a car, right? But how can you know? On the basis of figures, it would seem that there is insignificant effect, right? But it may be a real one, it may be because of multicoronarity. So अगर आपको multicoronarity का पता ना हो, you may be wrongly concluding that there is no effect of MPG on price, right? But if you check for multicoronarity, and then you are sure that this insignificant T ratio corresponding to MPG, right? If you are sure that this insignificant T ratio corresponding to MPG is not because of the problem of multicoronarity, तो फिर आप कह सकते हैं, okay, I was expecting significant effect, but according to my analysis, it is not. So the point that I'm telling you, that if you fit a model, as a researcher, you would be expecting significant effect of your explanatory variables, but somehow if you get insignificant results for your model, don't be just settling with that. Always check for multicoronarity. I repeat, always check for multicoronarity. यानी कहीं ऐसा तो नहीं है कि ये multicoronarity की वजह से आ रहा है, ठीक है? Another consequence of the multicoronarity is this one, that the R square may be very high, but very few T ratios may be significant. Before I can show you in using stata, let me just quickly go to a particular example here. Okay, forget about the details for the time being. I just want to show you the output. In this outcome, if you look at R square, this one, okay, you see, R square is fantastic, 0.8143, okay? But you see, if you look at the T ratio corresponding to X2, which is the ratio of the coefficient 0.4014 divided by the standard error 0.2721, this T ratio, it is insignificant. And if you look at the other T ratio, it is also insignificant. So this is one example of a model in which if you fit the model, the R square is 0.8143, 81.43% of the total variations in Y is explained or due to x2 and x3 together, right? So the R square value is not bad, but if you look at the individual T ratios, it is telling you that the effect of x2 on y is insignificant, and the effect of x3 on y is also insignificant, right? If you fit a model and you are having a model, a result like this, that R square is high, but none of the explanatory variable has any significant effect on the y variable, then this is considered to be one very common uh, indicator of multicoronarity, right? It may not always be the case, but you should suspect that there may be multicoronarity in my model, right? Never take it as it is. Again, I'm repeating, if you fit a model, your fitted model gives you a very high R square or a very good R square, just like in this case. It may not be very high, but by any standard, it is more than 80%. So therefore, it is okay, right? But you see, the T ratios, the T ratio corresponding to x2 is 1.4752, which, if you remember the 2T rule, is insignificant. So a high R square, but none of the T ratio is significant, right? And the reason is that the correlation between x2 and x3 here, you see, is 0.8285. Although for the time being, I'm not saying that how can I say that this is a high correlation, although apparently it's a very high value of R correlation, right? But for the time being, again, I'm not saying that how you determine whether this is a high value or smaller value, but apparently 0.8285 is a number which is comparatively close to +1, right, as compared to 0. So therefore, you can say because of this thing, right, you are getting a good R square, right? But if you look at the T ratios here, and if you look at the T ratio here, they are not that much good. So this is actually what we say a contradiction. And usually this should be considered as one particular indication of the possible presence of autocorrelation, okay? And sensitivity of OLS estimators and their standard errors to small changes in data. This means that if you make a slight change in your data set, I would leave these particular slides to you so that you can see yourself, right? What they have done, they have taken a data set, hypothetical data set, in which y is dependent variable and x2, x3 are independent variables, and they have fitted a model, and they have got this particular result, okay? This particular result in which these are the OLS estimates. 0.4463 is the OLS estimate associated with x2, and 0.0030 is the OLS estimate associated with x3. In the bracket, we have the standard errors of those estimators, and then in the next bracket, we have got the T ratios, which is the coefficient divided by the standard error, okay? So as you can see, if you have the 2T rule in mind, then the first T ratio is significant, which means the effect of x2 on y is significant. The second T ratio is actually not significant. R square is 0.81. This is actually based on table 10.3. Now, if you make a slight change, y remains the same, x2 remains the same, only a slight change is made here. You see, the two numbers in the x3 column, 12 at the third position and 0 at the fourth position, are interchanged. Apparently, one may say that it doesn't make that much difference. Like, for example, it's a slight change by just repositioning two values. 12 and zeros are interchanged. But if you fit a model on the basis of this slightly modified data, जिसको आप बज़ाहिर slight modification कह सकते हैं, right? when you fit the model and you compare it with the previous one, not only the OLS estimates and standard errors are affected, but the T ratios are also affected. Previously, the T ratio on the basis of first table was 2.41, which was significant, and now the T ratio is 1.4752, which is insignificant. So you see, just a slight change makes a lot of difference. This is called sensitivity of the OLS estimators towards slight change in the data. Okay, so therefore these are actually the consequences that you see. Okay, so how can you actually know that there is multicoronarity in my model? Let me just directly go to Stata, and I would like that we just do it together. Okay, so just open Stata if you have access to Stata, and let's fit a model and then check that model for multicoronarity. Okay, check that model for multicoronarity and then make our conclusion. Okay, so before you can check a model for multicoronarity, of course the first step is that you should fit the model. In the model fitting पहली चीज है. Checking for multicoronarity is then the post estimation process. यानी post estimation मतलब क्या है कि after you estimate the model, then you check it for multicoronarity. So let me fit a model in which price is a dependent variable. Okay, and for the time being I would keep it a little bit shorter. Let me take initially quantitative variables so that I can come to the qualitative variables data. Let me take MPG, headroom, trunk, weight, length, turn, displacement, gear ratio, right? 1, 2, 3, 4, 5, 6, 7, 8. Let me take the 8 quantitative variables from MPG to gear ratio, leaving for the time being rep 78 and foreign, right? Let me take and fit a model. Now, when I look at the model, although the R square for this model is not that much good, right? But the thing is that the model is on the whole significant. And when I just come down, I discover that weight, turn, and gear ratio are basically significant explanatory variables. But before I can decide to use this model, I say, okay, let me check this model for multicoronarity, which means एक चीज तो clear है ना कि because I have got the estimated model here, because I have got the model here, right? So it means that there is no case of perfect multicoronarity. अगर perfect multicoronarity का case होता, so I would not have obtained the estimated model. So therefore, the next thing is how to check this model. There are various approaches, okay, used for checking multicoronarity, but one approach is what we call the VIF approach, okay, which we call the variance inflation factor. So we determine the VIF associated with the OLS estimator of every explanatory variable. Okay, what is VIF, which stands for variance inflation factor? VIF represents the factor by which the variance of an OLS estimator is inflated or enhanced due to the presence of multicoronarity. In the presence of multicoronarity, how much the variance of an OLS estimator inflates or increases. Then the number of times that the factor by which it is increased is called the VIF. For example, just a hypothetical example, if the reported, which means estimated variance of let's say beta 1 hat, okay, suppose you fit a model and the variance of beta 1 hat which is actually the square of the standard error, is 5,000. Okay. But somehow you were expecting, just hypothetically imagine that the actual variance that you were expecting, or which should have been obtained, was 50, but instead of 50 you get actually 5,000. So you see there is a huge difference between the two. So we say 5,000 is a much bigger number as compared to 50. But then we discover that what is 5,000? 5,000 can be written as 100 times 50, right? What is 50? The original one, the expected one, which means that you can say that the reported figure, which is 5,000, is basically 100 times the actual variance. So we say that this 100 is basically the VIF. This is the variance inflation factor. We say that the actual variance of beta 1 hat has been inflated by a factor of 100, which means what you have got is actually an inflated variance. How much it has been inflated? You can say by a factor of 100. So it is 100 times more as compared to the original one. So this is actually the concept of VIF that we obtain, because multicoronarity deals with the inflation of variance, because when there is a case of high multicoronarity, we say that the variance of the OLS estimator increases. VIF is actually telling you how much increase is there, okay? How much increase is there. And then, by definition, VIF is defined like this, right? By definition, VIF is defined as 1 over 1 minus Rj square. 1 over 1 minus Rj square. What is Rj square? Rj square is the auxiliary R square of the auxiliary regression of Xj on all others, right? What we mean by all this terminology, for example, VIF1, when you are talking about x1, the first explanatory variable, you will be calculating. Keep in mind that there would be as many VIF values in our model as the number of explanatory variables in our model. अगर 2 explanatory variables हैं तो 2 VIF value होंगी, अगर 3 हैं तो 3 होंगी. So VIF1 means that I'm talking about calculation of the variance inflation factor corresponding to the coefficient of x1, which means corresponding to beta 1 hat. So it is calculated as 1 minus R1 square. What is R1 square? It is the R square obtained after regressing x1 on other x variables. अगर आप x1, which is basically an explanatory variables, if you treat this one temporarily as a dependent variable, and you fit a model in which you study the dependence of x1 on all other explanatory variables, this is what we call auxiliary regression, right? And the R square obtained from the regression of x1 on all other x variables will be denoted by R1 square. And when you put it into this formula, 1 over 1 minus R1 square, you will get the VIF1. Similarly for x2, right? VIF2 would be obtained as 1 over 1 minus R2 square, okay? Where R2 square would be the R square obtained after regressing x2 on all other x variables. What is the range of VIF? The minimum value is 1 and the maximum value can be any number. So it is from 1 up to infinity, right? And as I will explain in a moment, when VIF is 1, okay, which means when you say that the reported variance is 5,000 and the actual was also 5,000. So what is this actual? This would be 1 times the actual, which means if VIF is 1, it means there is no inflation, which means no multicoronarity has occurred. So how can you do it in Stata? After fitting this model, simply type VIF, right? simply type VIF in the command window, and you will get an outcome like this on the screen, right? So you see, now look at these numbers. These show the VIF, and these VIF values are arranged in the form of their size, right? Although the first explanatory variable in our model was MPG, the second one was headroom, right? But as you can see, weight is written first here because the VIF calculated corresponding to weight is the highest. So therefore, it has been sorted just to make it easy. So the VIF value corresponding to weight is 16.11. What does it mean? That the variance of the OLS estimator associated with the variable weight, right, is inflated by a factor of 16.11, which means that the reported variance corresponding to weight, what would be that variance? It would be the square of this number. This is the standard error, right? This is standard error. The square of this number, 1.363489, this would be the variance of the OLS estimator corresponding to weight. If you take the square of this, whatever is the number, this number 16.11 is actually saying that that figure, the square of this number, is actually 16.11 times more than the actual, right? So therefore, the variance of the OLS estimator associated with weight is 16.11 times more than the actual. That of the length is 12.85 more than the actual. So you see, none of the number in this list is exactly 1, which means that corresponding to each regressor, there is an inflation in variance. Some inflation is more, like corresponding to weight, while some is quite low, corresponding to headroom. Now the question is, how can you determine whether there is a case of high multicoronarity or not? So as a rule of thumb, any VIF value, okay, which exceeds 10, although when it is more than 1, it shows, but the VIF rule says, which is usually in some studies, people say if VIF is greater than 5, but majority of the study says that any VIF value which is greater than 10, then this shows a case of high multicoronarity, which means any number in this list which is more than 10 would show that that particular variable, like in this case the variable weight and the variable length, okay, two numbers in this list are more than 10, while the rest are actually less than 10. So although there is inflation in case of every variable, but two numbers are actually more than 10. So you would say that the variable weight is highly correlated with all other variables, and similarly the variable length is highly correlated with all other variables. In the language of econometrics, we would say that two variables, weight and length, are highly collinear with other variables, okay? And therefore, we would say that there is a case of high multicoronarity in this particular model. So you should not use this model as it is. Why? Because this model is suffering from a case of high multicoronarity. Now, what would be the solution? I mean, what should you do so that this problem is solved? Although in other lecture I will tell you something more about that, but right now I can tell you that one solution that people usually do is to drop the highly collinear variable, right? Drop one or more highly collinear variables from the model, okay? So, for example, using this suggestion, dropping the highly collinear variables. Like for example, if I drop weight and length from this model, which means if I refit a model in which weight and length is not there, what would happen? Let me just bring, by clicking this line from the review window, I'm bringing the command of the model again. But what I would do, I would just delete two variables from this list, right? This is like refitting a model without the two highly collinear variables, weight and length. So weight and length would not be there, all others are there. Let me fit the model. So this is a model without the two highly collinear variables, which I have dropped. Now I should check the VIF for this model and see whether any VIF value is more than 10 or not. So again, I would just type VIF here. Okay. So for example, I would just click VIF from the review window or type VIF in the command window. Okay. Now you see what is happening. All the VIF values, you see, all the VIF values are perfectly all right, which means none of them is less than more than 10. So therefore, one way would be that this model that you have fitted can be considered. But then you can also think of one more thing before you can decide. You can also say, is it necessary that I should drop both? Because maybe dropping of variable is an easy option, but it may not always be a desirable option. क्योंकि हो सकता है आप ये कहें कि one or more variable that I am dropping from my model, maybe that is actually a significant or important variable for your research. तो क्या आपको उसको drop करना चाहिए just because of multicoronarity? So I would say, let me fit a model by dropping only one of the two, right? जो दो वेरिएबल्स मैंने ड्रॉप किए थे ना, वेट और लेंथ, अब मैं कहूंगा कि इसमें से मैं एक को ड्रॉप करता हूं और एक को कीप करता हूं. And what is the situation then? So for example, I would bring the full model here in which weight and length are there, और फिलहाल मैं इसमें से वेट को वो करता हूं, डिलीट करता हूं, which means I am fitting a model in which all other explanatory variables are there except weight. देखें length इसमें है, but weight को मैंने drop किया. So keeping length and dropping weight, so dropping only weight, not both. I fit this model, right? Length is there, weight is not there. If I check the VIF for this model, by typing VIF after fitting this model, you see, again, no problem. All the VIF values are perfectly all right according to the rule. All of them are. So it means it's not necessary that I drop both weight and length. अगर मैं सिर्फ weight को drop कर दूं, length is there, but it is no more highly collinear. And then, interestingly, if I drop length and keep weight, you see, if I drop the length and weight is kept in the model, so that I get a model with weight but not length. And now check the VIF. Again, there is no problem, as you see. Although weight is there, but in contrast to the previous case, when it was actually with weight and length were both there, so the VIF for weight was 16.11. But when length is dropped, the VIF for weight comes down to 9.81, permissible, right? Perfectly okay. So what is our conclusion? Conclusion is that it's not necessary that you drop all the highly collinear variables from your model. right? You can drop only few. Like for example, in this case, you can drop one of them and the problem is still solved. Now, the last thing that we would decide, if it is, if the model is going to be okay by dropping only one of the highly collinear variable rather than both, which one we should drop, okay? Here, the researcher would use his or her priorities as well as the outcome of the original model. या तो आप खुद अपने priorities पे decide कर लें कि although you would like that both length and weight should be there, but when both are there, your model is suffering from the consequences of high multicoronarity. When one of them is dropped, then the problem is solved. Then you, as a researcher, can decide whether length is more important for you as compared to weight, or whether weight is more important for you as compared to length, right? Which one you can take risk to drop and which one you would like to keep. तो या तो आप ये कर लें, या दूसरा statistical consideration ये हो सकता है कि you can just look at the original model that you have fitted here, and you can say that in the original model, which was suffering from multicoronarity, weight is highly significant. The effect of weight is highly significant, while the effect of length is not significant. When weight is dropped and length is there, then length is still insignificant. But when length is dropped and weight is kept in the model, then weight is still significant. So statistically, for example, we would say that if it is to drop one of the two, then why should you drop a significant explanatory variable? If otherwise there is no justification, then statistically it would be better that you keep the significant variable weight inside the model and drop the insignificant variable length from the model. Okay, so this is actually what you can decide. So VIF is the approach used for detection of multicoronarity, and I have discussed one remedy with you today, in which is dropping the highly collinear variable. Remember, dropping the highly collinear variable is just one particular solution, one particular remedy. This may not always be an ideal remedy. यानी बहुत सारे cases में the researcher would not like to drop variables, right? In the next lecture, we will decide situations where you may not drop any of the highly collinear variable and your model would still be okay, right? Although there will be some other problems associated with those approaches, लेकिन आप जरूरी नहीं कि आप सिर्फ ये option use कर लें. लेकिन initially, I have discussed this solution because this is the easiest. So अगर otherwise, as a researcher, there is no problem for you by dropping one or more of the highly collinear variable. Just go for this because this is the easiest of all. With this, we would end the lecture. Okay. I hope the things are clear to you.
Yes, sir. Excuse me, sir.
जी जी.
ये तो क्लियर है सर. ये अभी ऑफ हो रहा है few सेकंड में, तो एग्जाम के हवाले से, पेपर के हवाले से अगर आप.
Okay, let me quickly, because I have already uploaded the paper, but you will be able to, of course,
Yes, sir. On the same
day of the exam,
whatever schedule.
right? There are 4 questions in your paper. You have to attempt 3 of your choice. एक का आपके पास choice है, right?
Yes.
There are 4 questions in total. Part A of each question would be a little bit descriptive, जिसमें simply आपसे कुछ थोड़े ideas के मुताबिक पूछा जाएगा कि आपको पता हो कि, for example, what is this, what is that, etc. And part B, this is important. You should all listen. Part B is requiring that you should choose a data set of your choice, right? And fit a model according to the statement which is given over there.